Hello and welcome to Physics Teacher. In this tutorial, I'm going to be going over redox reactions, which is a unit in the grade 12 chemistry class. I'm going to be going over quite a few things. The first is going to be how to balance a redox reaction. I'm going to be going over this fairly quickly, sort of like a review, but if you need help with balancing, I recently released an entire tutorial just for balancing, where I go over multiple examples and multiple methods. So if you want to take a look at that, go check out that as well. You can find it in the playlists on my channel for grade 12 chemistry. Then I'll be going over how to determine whether or not a redox reaction will be spontaneous. We'll do a couple examples of that. And then we're going to go over galvanic cells. We're going to draw some. We're going to look at half reactions and how to determine a cell's electric reduction potential. And finally, we're going to go over some redox reaction stoichiometry problems. All right, so let's get back to how are we going to balance a redox reaction. So redox reaction involves electron transfers. If you lose electrons, then that is considered oxidation. And if you gain electrons, that's considered reduction. So let's look at some of the oxidation numbers in this reaction here. So to determine the numbers, well, we can look at oxygen. Oxygen will have a charge of -2. Unless it's a peroxide, in which it will have a charge of -1. So this molecule right here has a total charge of -2. So what's going to be the charge on each chromium? So let's think of it like this. We have 2 chromium atoms with an unknown charge, let's call X. And then we have 7 oxygen atoms, each of them having a charge of -2. And when we take the total charge, we should end up with -2 charge. There's a little bit of math involved, but what would X be? So we have 2X minus 14 must equal -2. So we have a total -14 charge with the 7 oxygens. And this must be a total of 12, positive 12, for the total charge to sum up to -2. Therefore, each chromium atom will have a charge of +6 because we have 2 of them, which gives us a total of +12. All right, so we can see that the chromiums here each have a charge of +6, but after the reaction is complete, it says right here, they only have a charge of +3. So what happened? So we have a transfer of electrons, but specifically with chromium, did we lose or gain electrons? So think of it like this. I have a lot of students that get confused with this concept because it looks like you're losing electrons because you go from 6 to 3, right? But don't think of it mathematically like subtracting 3, right? If an object is neutral, that means it has the same number of positive charges and negative charges, like this little box I drew. However, if it's positive, like this one here, will have a charge of +2, we have more positive charges. And if we lose 1 electron, then that changes to be more positive. So losing electrons gives you a more positive charge. If you have a less positive charge, you're gaining electrons. So in that case, you'd be getting more electrons added. Right? If we added 2 more, then it would go to +1. So in this case, going from +6 to +3, what happens is we are gaining 3 electrons. So if you're gaining electrons, this is called reduction. So chromium is being reduced. All right, well, let's look at our chlorine. Now over here we have chlorine. It tells us -1 right there, -1. Now over here, when we have just the elements on its own, that's a charge of 0. So what's happening to chlorine? Is it gaining or is it losing electrons? Right, so initially we have 1 more electron, and then we have a neutral charge. So same number of positive and negative charges. So that negative charge left. So we lost. So we lose 1 electron. And if you lose electrons, this is called oxidation. So chlorine is being oxidized while chromium is being reduced. Now, this was the first step required in order to balance this equation. You have to determine what all those oxidation numbers are and what electron transfers are actually occurring. The next thing that we're going to do is typical for balancing equations. We're just going to look at everything except for oxygen and hydrogen to see if the actual atoms are balanced. So over here, notice we have 2 chromiums, but over here, 1. So we're going to put a 2 right there, right, to balance the chromiums. Same with chlorine. Here we have 1 and here we have 2, so we're going to put a 2 here. Next thing we have to do is actually balance the electron transfer. We can't gain 3 electrons and lose 1 electron, right? Charge must be conserved. So whatever we gain, we must lose as well. So what I'm going to do is multiply this value by 3. So that way we gain 3 electrons and lose 3 electrons for each element that we're concerned with. So timesing by 3, this is going to become 6, because 2 times 3 is 6. And this was a 1, but 1 times 3 is just 3. All right, so let me rewrite this because it's getting a bit messy. All right, so I have it rewritten. The next thing we're going to do is we are going to balance oxygen. You probably noticed oxygen is not balanced yet. Now, in order to balance oxygen, we are going to add water molecules. Okay, so H2O. Now there's 1 oxygen per each water molecule, and since we have 7 oxygen in our reactants, we want 7 water molecules in our products. Now, yes, that means hydrogen is not balanced because we just added 14 hydrogens. So we're going to add 14 hydrogen ions into our reactants. And for an acid, that is as far as we need to go. So that is our balanced redox reaction. If you want to know what to do for bases or you want a different method of doing it, go check out my tutorial on just how to balance redox reactions. All right, so next we're going to look at how to determine whether or not a redox reaction will proceed spontaneously. And the first step to be able to do that is very similar to how we balanced. We need to first be able to identify what's being reduced and what's being oxidized. So let's look at our charges. So here we have sodium chloride. So sodium in here is going to have a charge of +1. And then by itself, just as an element, 0. So what happened? Did we gain or lose electrons? If we went from positive to less positive, we must have gained electrons. Specifically, we gained 1 electron. If you follow this little mnemonic of Leo says Ger, which my students much prefer over the one I came up with. So Leo says Ger. So losing electrons is oxidation. Gaining electrons is reduction. So this is being reduced. So we have sodium being reduced. So if you look at the chlorine, that is a -1 here. Over here it's 0. So chlorine is losing an electron. So if we lose 1 electron, losing electrons is oxidation. So chlorine is being oxidized. Now, if sodium is being reduced, we say it is the oxidizing agent. I know this is confusing. It's the opposite. And if chlorine is being oxidized, it's the reducing agent. So now that we know that sodium is the oxidizing agent and chlorine is the reducing agent, we're going to look at this chart, which is the relative strengths of oxidizing agent and reducing agent. Now we need to find each one. If you look right there, we have chlorine. So we find chlorine under the reducing agents. So it's right here, chlorine. Now we find sodium all the way down here, and we're looking under oxidizing agents for sodium, which is right here. Now, the spontaneity rule says that if the oxidizing agent on this chart is above the reducing agent, then the reaction will be spontaneous. However, if it's not, then it will not be spontaneous. So in this case, we have the reducing agent up here, which is clearly above our oxidizing agent. So this is not spontaneous, which for salt is a very good thing, that it doesn't spontaneously become sodium and chlorine gas. That would not be good. But let's look at our second example. Here we have a strip of aluminum in aqueous copper 2 chloride solution. So let's write this out. We're going to have aluminum, some strip of aluminum, so solid, inside a solution of copper 2 chloride. So we're going to have these copper ions. So copper, charges of +2, aqueous. Now, if we exchange these charges, we're going to have aluminum, but aluminum has a charge of +3. And then we're going to have copper as a solid. And I can just quickly balance it. So we'll have 2, 3, 2, and 3. All right, so that's balanced, but it's not super important to be able to balance it to determine whether or not this reaction will proceed spontaneously. What we need to do is figure out which is the oxidizing agent and which is the reducing agent. So aluminum goes from no charge to a +3 charge. So aluminum is therefore losing electrons. If it's losing electrons, it's oxidizing, which means therefore it is the reducing agent. In the case of copper, copper is going from +2 to 0, so it is gaining electrons. So that means it is being reduced, and therefore it is the oxidizing agent. All right, let's bring up our chart. All right, so under oxidizing agent, we are going to look for copper. All right, notice that this is copper, and this is copper, and this is copper. So there's a lot of coppers here, but which one do you use? You want to use the one that is +2 to 0. So that's this one in this case, right? +2 to 0. Okay, so that's our oxidizing agent. So our oxidizing agent is up here. Now let's look under reducing agents and find aluminum. And it looks like aluminum's all the way down here. So that's our reducing agent. So the spontaneity rule, here we have the oxidizing agent above the reducing agent, just like this. So yes, this one will be spontaneous. All right, let's move on to our next question. All right, so in this question, we're going to look at this galvanic cell, this nickel-lead galvanic cell. We're going to draw and label it. So let's see what the parts of this cell looks like. Then we're going to write the reduction and oxidation half reactions along with the overall reaction. And then we're going to determine the cell's electric reduction potential, or put another way, the voltage of the cell. So let's draw what this cell looks like. So right here, there's our cell. And right here, I am going to draw our porous barrier. So there's our porous barrier. Right, now we need a metal in each. So the first side, or the left side, we have nickel. So that's going to be our solid nickel. And the other side, we have lead. So that's going to be our solid lead. And then, of course, coming from these, we are going to have in solution our nickel aqueous ions and our lead aqueous ions. So on the left side, we have our anode. So here's our anode, and here's our cathode. Here's our barrier, just like we've drawn in the picture. So here's our anode, and here's our cathode. And electrons are going to flow from anode to cathode. So let's look at what's being reduced. So which is being reduced? Is it lead or is it nickel? So if electrons are going from the nickel to the lead, then the lead is what is gaining electrons. And if you gain electrons, you're being reduced. So our lead is being reduced. So we have these lead ions, plus we have some electrons. In this case, we're going to need 2 electrons to give us our solid lead. So that's being reduced. Now, nickel is losing those electrons. So if we're losing electrons, we are being oxidized. So nickel is being oxidized. So we've got solid nickel producing our ions and our electrons, which then go over to the cathode. Now, if we combine these together and write our overall reaction, so those are our 2 half reactions. Overall, this actually works out nicely because the charges are the same. So the 2 electrons will cancel. If it didn't work out nicely, then you would just need to multiply one equation or both equation by some integer so that the electrons, what you gain is what you lose. Okay. If you want to see me doing that, again, go over to that tutorial on how to balance redox reactions, because one of the methods I show you is how to balance using half reactions, which would be very important knowledge to come and be able to look at galvanic cells. So our overall reaction then, if we just add them, we have nickel. So nickel solid plus lead ions, forgot the AQ. It's going to give us nickel ions plus solid lead. All right, lastly, we have to determine the cell's electric reduction potential. So the electric reduction potential at SATP for the cell is going to equal the potential for what's being reduced minus the potential for what's being oxidized. How are we going to figure that out? Well, we're going to go back to our strengths table. So lead is being reduced, meaning it's our oxidizing agent. So let's look for lead on here. And we have it right here. And it has a potential of negative 0.13. So that's negative 0.13 volts. And then what's being oxidized is our reducing agent. So let's look for nickel. And here we have nickel at negative 0.26. So negative 0.26 volts. So that's a double negative. So it becomes a positive. So we have 0.13 volts plus 0.26 volts. So our cell's potential is 0.13 volts. All right, our last problem that we're going to do in this tutorial is a little cell reaction stoichiometry. So in this case, we need to determine the mass of chlorine produced when a 200 amp current flows for 24 hours through a cell containing molten sodium chloride. That's a down cell. At which electrode is the chlorine produced? So let me just quickly draw what this cell looks like. All right, so here you have your anode and your cathode, and typically electrons will go from your anode to your cathode. But if we had a power supply like we have here, a 200 amp power supply, with that power supply, we can get the electrons flow to go in the other direction. Now, when we use a power supply to reverse the direction of the electrons, this is no longer a galvanic cell, this is an electrolytic cell. And that also flips where the cathode and anode are. So now the cathode is actually over here, and the anode is over here. So we have our chlorine ions losing an electron, giving us our chlorine gas. And this is going to happen at the anode. So that is where it occurs, at the anode. Now if we just balance this, we're going to need 2 of these. and therefore each one's going to need an electron, so we're going to need 2 electrons. All right, so there's our equation that's going to help us solve this problem. Now for the electrons, that is moving with a current of 200 amps for a time of 24 hours. Now, to do some stoichiometry, we need to know the number of moles of electron. And this is the equation that we've learned in this unit. The number of moles for these electrons is your current times your time divided by Faraday's constant, where Faraday's constant is equal to 9.65 times 10 to the 4 coulombs, which is a unit of charge, per mole. Now time also needs to be in seconds, so we need to change hours into seconds. So we multiply by 60 and then multiply by 60 again. Gives us 8.64 times 10 to the 4 seconds. So now we can figure out the number of moles using that equation of electrons. So we have the current, 200 amps, times our time, 8.64 times 10 to the 4 seconds, divided by Faraday's constant, which is 9.65 times 10 to the 4 coulombs per mole. And if you want to see how the units work, well, an ampere, or current, is the amount of charge that passes by a certain cross-sectional area in your wire in some time t. Right? So if you replace this with coulombs per second, I should write that as seconds, not t. Coulombs per second, you can see our seconds cancel, our coulombs cancel, and we're left with units of moles. And we end up with 179 moles. So here we have our stoichiometry. So we have a 2-to-1 ratio to figure out how much chlorine we have. So 2-to-1 ratio. And that's going to equal the number of moles of our electrons. So 179 moles divided by the moles of chlorine. So when we rearrange this, we get the moles for chlorine. It's going to be 179 divided by 2. So I'm just doing a little cross multiplication there. And so we get 89.5 moles. Now we're almost done because we can figure out mass, because mass just equals our number of moles times molar mass. So we have 89.5 moles of chlorine multiplied by the molar mass of chlorine, which is 70.9 grams per mole. And remember, it's 70.9 because this is Cl2. So we have 2 chlorine atoms. So you have to make sure you accommodate for that in your calculations for the molar mass of chlorine. And we end up with 6.35 kilograms, or 6,350 grams. So I hope that helped. If you have any questions, let me know in the comments. And if you still need some help with balancing, go check out that other tutorial. Thanks for watching.